The occupancy of the energy bands in a semiconductor is set by the position of the Fermi level relative to the semiconductor energy band edges. Application of a source-to-substrate reverse bias of the source body p-n junction introduces a split between the Fermi levels for electrons and holes, moving the Fermi level for the channel further from the band edge, lowering the occupancy of the channel. The effect is to increase the gate voltage necessary to establish the channel, as seen in the figure. This change in channel strength by application of reverse bias is called the body effect. Using an NMOS example, the gate-to-body bias VGB positions the conduction band energy levels, while the source-to-body bias VSB positions the electron Fermi level near the interface, deciding occupancy of these levels near the interface, and hence the strength of the inversion layer or channel. The body effect upon the channel can be described using a modification of the threshold voltage, approximated by the following equation. V sub Tb equals V sub T0 plus gamma times open paren the square root of V sub Sb plus 2 phi sub b minus the square root of 2 phi sub b close paren comma, where Vtb is the threshold voltage with substrate bias present, and Vt0 is the 0 Vsb value of threshold voltage. Gamma is the body effect parameter, and 2b is the approximate potential drop between surface and bulk across the depletion layer when Vsb equals 0 and gate bias is sufficient to ensure that a channel is present. As this equation shows, a reverse bias Vsb 0 causes an increase in threshold voltage Vtb and therefore demands a larger gate voltage before the channel populates. The body can be operated as a second gate, and is sometimes referred to as the back gate. The body effect is sometimes called the back gate effect. Circuit symbols, edit. A variety of symbols are used for the MOSFET. The basic design is generally a line for the channel with the source and drain leaving it at right angles and then bending back at right angles into the same direction as the channel. Sometimes 3 line segments are used for enhancement mode and a solid line for depletion mode. See depletion and enhancement modes. Another line is drawn parallel to the channel for the gate. The bulk or body connection, if shown, is shown connected to the back of the channel with an arrow indicating PMOS or NMOS. Arrows always point from P to N, so NMOS, N channel in P well or P substrate, has the arrow pointing in, from the bulk to the channel. If the bulk is connected to the source, as is generally the case with discrete devices, it is sometimes angled to meet up with the source leaving the transistor. If the bulk is not shown, as is often the case in IC design as they are generally common bulk, an inversion symbol is sometimes used to indicate PMOS. Alternatively, an arrow on the source may be used in the same way as for bipolar transistors, out for NMOS, in for PMOS. Comparison of enhancement mode and depletion mode MOSFET symbols, along with JFET symbols. The orientation of the symbols, most significantly the position of source relative to drain, is such that more positive voltages appear higher on the page than less positive voltages, implying conventional current flowing down the page. P channel, N channel, JFET MOSFET N, MOSFET N, no bulk, MOSFET dip. In schematics where G, S, D are not labeled, the detailed features of the symbol indicate which terminal is source and which is drain. For enhancement mode and depletion mode MOSFET symbols, in columns 2 and 5, the source terminal is the one connected to the triangle. Additionally, in this diagram, the gate is shown as an L shape, whose input leg is closer to S than D, also indicating which is which. However, these symbols are often drawn with a T-shaped gate, as elsewhere on this page, so it is the triangle which must be relied upon to indicate the source terminal. For the symbols in which the bulk, or body, terminal is shown, it is here shown internally connected to the source, i.e., the black triangles in the diagrams in columns 2 and 5. This is a typical configuration, but by no means the only important configuration. In general, the MOSFET is a 4-terminal device, and in integrated circuits many of the MOSFETs share a body connection, not necessarily connected to the source terminals of all the transistors. Applications, edit. Digital integrated circuits such as microprocessors and memory devices contain thousands to billions of integrated MOSFET transistors on each device, providing the basic switching functions required to implement logic gates and data storage. Discrete devices are widely used in applications such as switch mode power supplies, variable frequency drives and other power electronics applications where each device may be switching thousands of watts. Radio frequency amplifiers up to the UHF spectrum use MOSFET transistors as analog signal and power amplifiers. Radio systems also use MOSFETs as oscillators, or mixers to convert frequencies. MOSFET devices are also applied in audio frequency power amplifiers for public address systems, sound reinforcement and home and automobile sound systems. MOS integrated circuits, edit. Following the development of clean rooms to reduce contamination to levels never before thought necessary, and of photolithography and the planar process to allow circuits to be made in very few steps, the SiO2 system possessed the technical attractions of low cost of production, on a per-circuit basis, and ease of integration. Largely because of these two factors, the MOSFET has become the most widely used type of transistor in the Institution of Engineering and Technology, IET. General Microelectronics introduced the first commercial MOS integrated circuit in 1964. Additionally, the method of coupling two complementary MOSFETs, P-channel and N-channel, into one high-forward/low switch, known as CMOS, means that digital circuits dissipate very little power except when actually switched. The earliest microprocessors starting in 1970 were all MOS microprocessors, i.e., fabricated entirely from CMOS logic or fabricated entirely from MOS logic. In the 1970s, MOS microprocessors were often contrasted with CMOS microprocessors and bipolar bit slice processors. CMOS circuits, edit. The MOSFET is used in digital complementary metal oxide semiconductor, CMOS, logic, which uses P and N channel MOSFETs as building blocks. Overheating is a major concern in integrated circuits since ever more transistors are packed into ever smaller chips. CMOS logic reduces power consumption because no current flows, ideally, and thus no power is consumed, except when the inputs to logic gates are being switched. CMOS accomplishes this current reduction by complementing every NMOSFET with a PMOSFET and connecting both gates and both drains together. A high voltage on the gates will cause the NMOSFET to conduct and the PMOSFET not to conduct, and a low voltage on the gates causes the reverse. During the switching time, as the voltage goes from one state to another, both MOSFETs will conduct briefly. This arrangement greatly reduces power consumption and heat generation. Digital, edit. The growth of digital technologies like the microprocessor has provided the motivation to advance MOSFET technology faster than any other type of silicon-based transistor. A big advantage of MOSFETs for digital switching is that the oxide layer between the gate and the channel prevents DC current from flowing through the gate, further reducing power consumption and giving a very large input impedance. The insulating oxide between the gate and channel effectively isolates a MOSFET in one logic stage from earlier and later stages, which allows a single MOSFET output to drive a considerable number of MOSFET inputs. Bipolar transistor-based logic, such as TTL, does not have such a high fan-out capacity. This isolation also makes it easier for the designers to ignore to some extent loading effects between logic stages independently. That extent is defined by the operating frequency. As frequencies increase, the input impedance of the MOSFETs decreases. Analog, edit. The MOSFET's advantages in digital circuits do not translate into supremacy in all analog circuits. The two types of circuit draw upon different features of transistor behavior. Digital circuits switch, spending most of their time either fully on or fully off. The transition from one to the other is only of concern with regards to speed and charge required. Analog circuits depend on operation in the transition region where small changes to VGS can modulate the output, drain, current. The MOSFET and bipolar junction transistor, BJT, are preferred for accurate matching of adjacent devices in integrated circuits, higher transconductance and certain temperature characteristics which simplify keeping performance predictable as circuit temperature varies. Nevertheless, MOSFETs are widely used in many types of analog circuits because of their own advantages: zero gate current, high and adjustable output impedance, and improved robustness versus BJTs, which can be permanently degraded by even lightly breaking down the emitter base. The characteristics and performance of many analog circuits can be scaled up or down by changing the sizes, length and width of the MOSFETs used. By comparison, in bipolar transistors follow a different scaling law. MOSFET's ideal characteristics regarding gate current, 0, and drain source offset voltage, 0, also make them nearly ideal switch elements, and also make switched capacitor analog circuits practical. In their linear region, MOSFETs can be used as precision resistors, which can have a much higher controlled resistance than BJTs. In high-power circuits, MOSFETs sometimes have the advantage of not suffering from thermal runaway as BJTs do. This means that complete analog circuits can be made on a silicon chip in a much smaller space and with simpler fabrication techniques. MOSFET are ideally suited to switch inductive loads because of tolerance to inductive kickback. Some ICs combine analog and digital MOSFET circuitry on a single mixed signal integrated circuit, making the needed board space even smaller. This creates a need to isolate the analog circuits from the digital circuits on a chip level, leading to the use of isolation rings and silicon on insulator, SOI. Since MOSFETs require more space to handle a given amount of power than a BJT, fabrication processes can incorporate BJTs and MOSFETs into a single device. Mixed transistor devices are called bifets, bipolar FETs, if they contain just one BJT FET, and bi-CMOS, bipolar CMOS, if they contain complementary BJT FETs. Such devices have the advantages of both insulated gates and higher current density. Analog switches, edit. This section does not cite any sources. Please help improve this section by adding citations to reliable sources. Unsourced material may be challenged and removed. September 2016. Learn how and when to remove this message. MOSFET analog switches use the MOSFET to pass analog signals when on, and as a high impedance when off. Signals flow in both directions across a MOSFET switch. In this application, the drain and source of a MOSFET exchange places depending on the relative voltages of the source and drain electrodes. The source is the more negative side for an NMOS or the more positive side for a PMOS. All of these switches are limited on what signals they can pass or stop by their gate source, gate drain and source drain voltages. Exceeding the voltage, current, or power limits will potentially damage the switch. Single type, edit. This analog switch uses a 4-terminal simple MOSFET of either P or N type. In the case of an N-type switch, the body is connected to the most negative supply, usually GND, and the gate is used as the switch control. Whenever the gate voltage exceeds the source voltage by at least a threshold voltage, the MOSFET conducts. The higher the voltage, the more the MOSFET can conduct. An NMOS switch passes all voltages less than VGT/VTN. When the switch is conducting, it typically operates in the linear, or ohmic, mode of operation, since the source and drain voltages will typically be nearly equal. In the case of a PMOS, the body is connected to the most positive voltage, and the gate is brought to a lower potential to turn the switch on. The PMOS switch passes all voltages higher than VGT/VTP. Threshold voltage VTP is negative in the case of enhancement mode PMOS. Dual type, CMOS, edit. This complementary or CMOS type of switch uses one PMOS and one NMOS FET to counteract the limitations of the single type switch. The FETs have their drains and sources connected in parallel. The body of the PMOS is connected to the high potential, VDD, and the body of the NMOS is connected to the low potential, GND. To turn the switch on, the gate of the PMOS is driven to the low potential and the gate of the NMOS is driven to the high potential. For voltages between VDD/VTN and GND/VTP, both FETs conduct the signal. For voltages less than GND/VTP, the NMOS conducts alone, and for voltages greater than VDD/VTN, the PMOS conducts alone. The voltage limits for this switch are the gate source, gate drain and source drain voltage limits for both FETs. Also, the PMOS is typically 2 to 3 times wider than the NMOS, so the switch will be balanced for speed in the two directions. Tri-state circuitry sometimes incorporates a CMOS MOSFET switch on its output to provide for a low ohmic, full range output when on, and a high ohmic, mid-level signal when off. Construction, edit. Gate material, edit. The primary criterion for the gate material is that it is a good conductor. Highly doped polycrystalline silicon is an acceptable but certainly not ideal conductor, and also suffers from some more technical deficiencies in its role as the standard gate material. Nevertheless, there are several reasons favoring use of polysilicon. 1. The threshold voltage, and consequently the drain to source on current, is modified by the work function difference between the gate material and channel material. Because polysilicon is a semiconductor, its work function can be modulated by adjusting the type and level of doping. Furthermore, because polysilicon has the same bandgap as the underlying silicon channel, it is quite straightforward to tune the work function to achieve low threshold voltages for both NMOS and PMOS devices. By contrast, the work functions of metals are not easily modulated, so tuning the work function to obtain low threshold voltages, LVT, becomes a significant challenge. Additionally, obtaining low threshold devices on both PMOS and NMOS devices sometimes requires the use of different metals for each device type. 2. The silicon SiO2 interface has been well studied and is known to have relatively few defects. By contrast, many metal insulator interfaces contain significant levels of defects which can lead to Fermi-level pinning, charging, or other phenomena that ultimately degrade device performance. 3. In the MOSFET IC fabrication process, it is preferable to deposit the gate material prior to certain high-temperature steps in order to make better performing transistors. Such high-temperature steps would melt some metals, limiting the types of metal that can be used in a metal gate-based process. While polysilicon gates have been the de facto standard for the last 20 years, they do have some disadvantages which have led to their likely future replacement by metal gates. These disadvantages include: 1. Polysilicon is not a great conductor, approximately 1,000 times more resistive than metals. which reduces the signal propagation speed through the material. The resistivity can be lowered by increasing the level of doping, but even highly doped polysilicon is not as conductive as most metals. To improve conductivity further, sometimes a high-temperature metal such as tungsten, titanium, cobalt, and more recently nickel is alloyed with the top layers of the polysilicon. Such a blended material is called silicide. The silicide-polysilicon combination has better electrical properties than polysilicon alone and still does not melt in subsequent processing. Also, the threshold voltage is not significantly higher than with polysilicon alone, because the silicide material is not near the channel. The process in which silicide is formed on both the gate electrode and the source and drain regions is sometimes called salicide, self-aligned silicide. 2. When the transistors are extremely scaled down, it is necessary to make the gate dielectric layer very thin, around 1 nm in state-of-the-art technologies. A phenomenon observed here is the so-called polydepletion, where a depletion layer is formed in the gate polysilicon layer next to the gate dielectric when the transistor is in the inversion. To avoid this problem, a metal gate is desired. A variety of metal gates such as tantalum, tungsten, tantalum nitride, and titanium nitride are used, usually in conjunction with high dielectrics. An alternative is to use fully silicided polysilicon gates, a process known as fusing. Present high-performance CPUs use metal gate technology, together with high dielectrics, a combination known as high metal gate, HKMG. The disadvantages of metal gates are overcome by a few techniques. 1. The threshold voltage is tuned by including a thin work function metal layer between the high dielectric and the main metal. This layer is thin enough that the total work function of the gate is influenced by both the main metal and thin metal work functions, either due to alloying during annealing, or simply due to the incomplete screening by the thin metal. The threshold voltage thus can be tuned by the thickness of the thin metal layer. 2. High dielectrics are now well studied, and their defects are understood. 3. HKMG processes exist that do not require the metals to experience high temperature anneals. Other processes select metals that can survive the annealing step. Insulator, edit. As devices are made smaller, insulating layers are made thinner, often through steps of thermal oxidation or localized oxidation of silicon, locus. For nanoscale devices, at some point tunneling of carriers through the insulator from the channel to the gate electrode takes place. To reduce the resulting leakage current, the insulator can be made thinner by choosing a material with a higher dielectric constant. To see how thickness and dielectric constant are related, note that Gauss's law connects field to charge as Q equals kappa epsilon sub 0 E, with Q equals charge density, kappa equals dielectric constant, 0 equals permittivity of empty space and E equals electric field. From this law it appears the same charge can be maintained in the channel at a lower field provided kappa is increased. The voltage on the gate is given by V sub cap G equals V sub CH plus E times T sub INS equals V sub CH plus QT sub INS over kappa epsilon sub 0, with VG equals gate voltage, VCH equals voltage at channel side of insulator, and tins equals insulator thickness. This equation shows the gate voltage will not increase when the insulator thickness increases, provided kappa increases to keep tins / kappa equals constant. See the article on high dielectrics for more detail, and the section in this article on gate oxide leakage. The insulator in a MOSFET is a dielectric which can in any event be silicon oxide, formed by locus, but many other dielectric materials are employed. The generic term for the dielectric is gate dielectric, since the dielectric lies directly below the gate electrode and above the channel of the MOSFET. Junction design, edit. The source-to-body and drain-to-body junctions are the object of much attention because of three major factors. Their design affects the current voltage, IV, characteristics of the device, lowering output resistance, and also the speed of the device through the loading effect of the junction capacitances, and finally, the component of standby power dissipation due to junction leakage. The drain-induced barrier lowering of the threshold voltage and channel length modulation effects upon IV curves are reduced by using shallow junction extensions. In addition, halo doping can be used, that is, the addition of very thin heavily doped regions of the same doping type as the body tight against the junction walls to limit the extent of depletion regions. The capacitive effects are limited by using raised source and drain geometries that make most of the contact area border thick dielectric instead of silicon. These various features of junction design are shown, with artistic license, in the figure. Scaling, edit. This section is written like a personal reflection, personal essay, or argumentative essay that states a Wikipedia editor's personal feelings or presents an original argument about a topic. Please help improve it by rewriting it in an encyclopedic style. September 2016. Learn how and when to remove this message. Further information, Dennard scaling. Over the past decades, the MOSFET, as used for digital logic, has continually been scaled down in size. Typical MOSFET channel lengths were once several micrometers, but modern integrated circuits are incorporating MOSFETs with channel lengths of tens of nanometers. Robert Dennard's work on scaling theory was pivotal in recognizing that this ongoing reduction was possible. Intel began production of a process featuring a 32 nm feature size, with the channel being even shorter, in late 2009. The semiconductor industry maintains a roadmap, the ITRS, which sets the pace for MOSFET development. Historically, the difficulties with decreasing the size of the MOSFET have been associated with the semiconductor device fabrication process, the need to use very low voltages, and with poorer electrical performance necessitating circuit redesign and innovation. Small MOSFETs exhibit higher leakage currents and lower output resistance. Smaller MOSFETs are desirable for several reasons. The main reason to make transistors smaller is to pack more and more devices in a given chip area. This results in a chip with the same functionality in a smaller area, or chips with more functionality in the same area. Since fabrication costs for a semiconductor wafer are relatively fixed, the cost per integrated circuits is mainly related to the number of chips that can be produced per wafer. Hence, smaller ICs allow more chips per wafer, reducing the price per chip. In fact, over the past 30 years the number of transistors per chip has been doubled every 2-3 years once a new technology node is introduced. For example, the number of MOSFETs in a microprocessor fabricated in a 45 nm technology can well be twice as many as in a 65 nm chip. This doubling of transistor density was first observed by Gordon Moore in 1965 and is commonly referred to as Moore's law. It is also expected that smaller transistors switch faster. For example, one approach to size reduction is a scaling of the MOSFET that requires all device dimensions to reduce proportionally. The main device dimensions are the channel length, channel width, and oxide thickness. When they are scaled down by equal factors, the transistor channel resistance does not change, while gate capacitance is cut by that factor. Hence, the RC delay of the transistor scales with a similar factor. While this has been traditionally the case for the older technologies, Therefore the state-of-the-art MOSFET's reduction of the transistor dimensions does not necessarily translate to higher chip speed because the delay due to interconnections is more significant. Producing MOSFETs with channel lengths much smaller than a micrometer is a challenge, and the difficulties of semiconductor device fabrication are always a limiting factor in advancing integrated circuit technology. Though processes such as ALD have improved fabrication for small components, the small size of the MOSFET, less than a few tens of nanometers, has created operational problems.